Hello class, these are our notes for Calc AB. Today we are looking at section 8.7, Indeterminate Forms and L'Hopital's rule. So we're going to start out by considering a limit that we would have done before. So we have a limit as x approaches 2 of x squared minus 4 over x minus 2. So our first instinct for limits is always just to do a direct substitution. And by direct substitution, I mean we're just going to take our limit number 2 and we're going to substitute that. So 2 squared minus 4 over 2 minus 2. The problem is we really quickly see that this makes 0 over 0. And so we can't use direct substitution. So if we think about our algebraic methods for something like this were to go ahead and just factor. So let's go ahead and make this the limit as x approaches 2. Let's see, we can factor this to x minus 2 times x plus 2. And then because we have an x minus 2 factor in common, we can make it the limit as x approaches 2 of just x plus 2. And now we can directly substitute, and 2 plus 2 makes 4. So our issue with this one, the reason that we couldn't use direct substitution is that we had 0 over 0. That's one of our indeterminate forms. So indeterminate forms are 0 over 0, infinity over infinity, negative infinity over negative infinity over positive infinity, something like that. We also want to do a quick review of mean value theorem. You're going to see that this is kind of where, I don't know what I just did. Mean value theorem is kind of where our new L'Hopital's rule is going to come from. So mean value theorem just said that our slope at a point, and so we're going to call that f prime of c, because at a point, it's the derivative, is equal to the slope of the endpoints. And if we're looking at 2 points A and B, this would be f of B minus f of A over B minus A. So if I was going to set up some kind of a function over here, this is going to be my A, this is going to be B, so this point would be A comma f of A, this point would be B comma f of B, and the slope of the endpoints would be, if I draw a line through here, remember slope is rise over run, it's how that line is angled. So there's going to be some point C that when I draw my line through C, my slope at a point, my tangent line, they have the same slope. So these two lines are parallel. And so then this point is going to be C comma f of C. So that was our mean value theorem. So the extended mean value theorem is what we're using to get this L'Hopital's rule. So L'Hopital's rule, what it's basically doing is it's saying, hey, we might have an infinity over infinity for our direct substitution, right? It may be something like this. It's this indeterminate form, but are they both going to infinity at the same rate? So the idea is if we want to look at how fast something's going to infinity, that we're really taking, and it's 0 over 0. It works for all of these, right? But infinity over infinity is the one I think makes the most sense. So by taking the derivative, you're really looking at like a rate. And so it's allowing you to compare the numerator and denominator, because if one is going to infinity a lot faster than the other, then there could be like a ratio between those two. So another thing we want to add here, it works really well for transcendental functions, especially these are not polynomials. This is like lots of different stuff that's going together. And that would be like logs or natural log, right? Trig, e to the x power, a to the x power. So these would all be like not polynomial, so transcendentals. Okay, so putting this all together. So L'Hopital's basically says if I am trying to find the limit of a function, the function has a numerator and denominator, remember, and it's indeterminate. So this is if indeterminate. can only use it if it's indeterminate, then instead I can look at the limit of the derivative of the numerator over the derivative of the denominator. So essentially I'm comparing those rates. So if it's indeterminate, L'Hopital, take a derivative on the top and bottom and then see what happens. So let's go ahead and look at the first one. So first we want to look at direct substitution. So if I do a direct substitution, I would have e to the 2 times 0 power minus 1 over 0. E to the 0 power is 1, so I get 1 minus 1 over 0. That's 0 over 0. So this is indeterminate. So because it's indeterminate, you have to show this work that we've got indeterminate, I can use L'Hopital's rule. And so L'Hopital's rule says keep this limit as x approaches 0, but take your derivative on the top and bottom. So my derivative of the numerator, I know e to the power is still e to the power, but I have to do chain rule. Derivative of 2x is 2, so it's going to be 2e to the 2x. This minus 1 is just going to become a 0 now. That's gone. And my denominator, the derivative of x, is just 1. So what I end up with now is just the limit as x approaches 0 of 2e to the 2x. So now that I don't have a denominator, I can substitute 0. So 2e to the 2 times 0 power. So e to the 0 is just going to be 1. So 2 times 1. And so my answer is 2. So it really kind of seems like magic. So again, I had to show it was indeterminate. So I did that. And then I said, I'm going to use L'Hopital's rule. And then I went through and I took a derivative and I did L'Hopital's rule. So those are kind of your steps that you've got to do. It works really well though, like we said, for these weird functions like e to the 2x power. For polynomials, I know we've got a lot of other strategies. We have algebraic strategies, but when we look at logs or trig or e to a power, something that's exponential, it's nice to have a different tool in your toolbox. So on the next one, I have natural log x over x. So what happens as x approaches infinity? Well, when I take a natural log of a bigger and bigger and bigger number, I just get a bigger and bigger and bigger number. So that's going to be infinity over infinity. So this is indeterminate again. So because we showed, and I probably want to write this, because we showed it's indeterminate, now I can say that I'm using L'Hopital's rule, and you have to say that for the AP test. And now I can go ahead and take a derivative. So my derivative of natural log x is 1 over x, over derivative of x is just 1. So I end up with just the derivative as x approaches infinity of 1 over infinity. Or sorry, 1 over x. I'm thinking ahead. And if I think about what happens as I get x to be a really, really big number, 1 over really big is just going to essentially be 0. So this limit is going to be 0. So again, L'Hopital's kind of works like magic. We had natural log. It was kind of weird. We didn't have any like algebraic steps that we could use. It's a transcendental function, natural log is, but we were able to find our limit this way with L'Hopital's rule again. All right, for 3, let's see, as x squared, as x approaches negative infinity, x squared would approach, well, we're squaring it, right? So it would approach infinity. And then our denominator, e to the negative infinity, so e to the positive infinity power, that's going to be something that's really, really big as well. So this is going to be infinity over infinity. So it is indeterminate. Because it's indeterminate, we are going to use L'Hopital's rule. So we have to show it's indeterminate, we have to write L'Hopital, and then we can actually apply it. So it's the limit as x approaches negative infinity, and then we're going to take our derivative on the top and bottom. Derivative of x squared is a 2x. Derivative of e to the negative x power, well, that's going to be e to the negative x times our derivative of negative x, which is just a negative 1. This is maybe a little bit weird with the negative exponent, so I think I'm going to rewrite it. It was helpful to have a fraction to look to see if it was indeterminate, but now I really don't want that fractional form. So I'm going to write this as negative 2x e to the negative x. And so what happens, you know what, I can't do anything with that still, can I? Is it still indeterminate? Let's check that out. because plugging in something there is still not going to help. So I reduced it from x squared to 2x, but I still have an x there. And so that means I would still have an infinity on top. And what would happen in the bottom? Negative e to the negative, so a negative e to the infinity, so it's negative infinity now. So it's still indeterminate. So if it's still indeterminate, I'm going to write L'Hopital again. Okay, so I feel like these check marks, I'm trying to show you that we're doing steps, but that's not really part of our work, so I'm going to go ahead and erase them. So it's still indeterminate, but when I apply a limit again, this time I'm not going to have an x anymore in the numerator. So I think now I'm going to be good. So it's essentially keeps reducing that power of x. So derivative of 2x is just going to be 2. And then my denominator, negative times negative, now I have just e to the negative x power. Okay, now I think I can do something with this. So this is going to be 2 over e. Actually, let's make it 2 times e to the x. That's really what it is, right? If it's a negative in the denominator, then it's positive. Okay. As e is to the negative exponent, it gets really, really big. So let's think about what happens with e to the negative infinity. That's a reciprocal. It's 1 over e to the infinity power. So it's basically like 1 over really, really big. So right now is we have, if we're doing our thinking, right, we have 2 times 1 over something really big. And so our limit here is just going to be 0. So we were able to get an answer, but we did have to do 2 L'Hopital rule, like we had to apply it twice. All right, this next one, I don't even have a fraction, but again, we've got e to the negative x power. It's a transcendental function. So let's try rewriting it as a fraction. I can't just plug infinity in there. It's going to be weird. So let's make it limit as x approaches infinity, and let's rewrite this, square root of x over e to the x. And let's go ahead and check now. If I put in infinity, square root of infinity, still infinity. E to the infinity power, still infinity. So we have something that's indeterminate. So because it's indeterminate, we're going to apply L'Hopital's rule. And we're going to take a derivative in the numerator and denominator. So our limit as x approaches infinity of, let's see, 1/2 x to the negative 1/2 power. This is just e to the x. So because this has a negative exponent, I want to shift it to the denominator. So limit as x approaches infinity. Really, I just have 1 in the numerator because the 2 can go in the denominator also. So I have 2, I have square root of x, and I have e to the x power. So let's think about what happens as x approaches infinity. This is going to be 1 over really big times really big. So 1 over a really big number, well, that's just going to be 0 again. All right, last two are a little bit of review. So this first one is a limit as x approaches infinity, but I have polynomials. So we have a lot of different strategies to work with polynomials. One of them was to divide. And this is 3, 5, and this is review, of course. And it was on page 200. I went through and looked at page numbers for you. So one of the limit techniques that we learned, it's funny, we did limits, I think 3 different times this year. At the beginning of the year, we used our basic pre-calc strategies, and then we got this strategy stuff kind of more in the middle of the year. And now we're doing L'Hopital's rule. So what we can do is we can look at the biggest power is x squared. And so we're going to go through and we're going to just divide all of the terms by x squared. So basically we're dividing by an x squared on the top and bottom, and then we're distributing that. And when we do that, what happens is, well, this x squared over x squared, right? That's just a 1. So we're kind of changing the way it looks. We have now the limit as x approaches infinity of 3 minus 1 over x squared over 2 plus 1 over x squared. And what happens is that these 1 over x squared guys, as x gets to be really, really big, those are just 0. So we're going to end up with 3 halves. So if we think about our direct substitution here, if I directly substituted infinity to start with, I would have 3 times infinity squared minus 1. Like this would just be an infinity over infinity situation. So instead of using our algebra stuff that we did earlier, some strategies we did earlier this year, we also could do L'Hopital's rule. So let's see how that works if we do L'Hopital's instead. So if we do L'Hopital's instead, we have the limit as x approaches infinity of, let's look at the numerator. If I take my derivative, I would have a 6x, the 1 is gone. My denominator, I would have a 4x. So x over x, like that's just makes it 1, right? I would have 6/4, which is 3/2. So L'Hopital's rule gives me the same answer, just a little bit faster. But I think it's really cool to see that both of those strategies work and how they're kind of connected. This next one, we did in section 1.3. This was page 65, and this was using this rule that none of you like, that was limit as x approaches 0 of sine x over x is equal to 1. And so one of the ways that we did this, so the technique basically was to say, well, I have a sine 3x, so like here I have an x over x, those have to match. So if I want there to be a 3x in the denominator as well, that means I need to multiply my numerator by 3. So I have 3 sine 3x over 3x. So I multiplied by 3 on the top and bottom. And then we took this 3 and we put it out in front. So we had 3 times the limit as x approaches 0 of sine 3x over 3x. And then we knew that that guy was just equal to 1, so we had 3 times 1 is just equal to 3. So let's go back to the beginning and think about what if I actually substituted 0 in. So that would be, sorry about that. This is twice in one notes. This is not good. So if we substitute in 0, we'd have sine of 3 times 0, that's just 0 over 0. And if I think about the sine of 0, that is just 0. So we have 0 over 0. It is indeterminate. So because it's indeterminate, I could actually also do L'Hopital's. And maybe we should make a note here, L'Hopital, because direct is 0 over 0. I'm just worried that, we won't look up here and then go, oh, that's why we did L'Hopital's. Same thing here, because direct is infinity over infinity. So because it's indeterminate, we can't do L'Hopital's again. So let's think about taking the derivative of sine. Well, derivative of sine is cosine, but chain rule means we also have to multiply it by 3. So we're going to have limit as x approaches 0 of 3 cosine 3x. Derivative of x is just 1, so it takes care of that denominator issue. So we have the limit as x approaches 0 of 3 cosine 3x. So now let's go ahead and directly substitute because we don't have a denominator anymore. So 3 times the cosine of 3 times 0 is just cosine 0. Well, the cosine of 0, so think about that point. The cosine of 0 is 1. The sine of 0 is 0, but the cosine of 0 is 1. So 3 times 1, which is just equal to 3. So I think this is really cool on these last two to see different methods that you can use. And again, it was using 1.3, page 65. We did that, but then also showed with L'Hopital's. This one was where we divided by the biggest power, but also used L'Hopital's, and they gave us the same answer. So the big idea today, I know I didn't really talk about how L'Hopital's comes from the extended mean value theorem. It was something I used to spend more time on, but I don't know that it's really worth it. I think the important thing is if it's indeterminate, and remember indeterminate means 0 over 0, some combination of infinity over infinity, negative or positive, whatever. But if it is indeterminate, then you can just take your derivative of the top and bottom and find the limit of that instead. So L'Hopital's rule is a real game changer. It takes other limits that we've been finding, it makes them a lot easier. And it's just pretty quick and easy. It's pretty cool. You have to check for indeterminate though first. So if you don't check for that, that's not going to get you points on an AP test or on anything we do in class. So first show indeterminate, and then if it's indeterminate, then you can go ahead and do L'Hopital's. All right, so as always, if you need help, please make sure you ask.